Yes, thank you. Hi, everyone. My name is Kate Storey-Fisher. I'm a postdoc at Stanford KaiPak, and I will be talking to you today about simulation-based inference from galaxy clustering with our library called muchisimocks. Someone in this room was trying to recall my talk title and dubbed it so many sims, like a lot of sims. So that's what I'll be telling you today about what you can do when you kind of get around this limitation of simulation-based inference. So a quick recap of the topic. Uh, Often when we do inference from galaxy clustering, we're doing a likelihood-based inference. And when you do this, you have a prior and you define some likelihood that you have to typically assume is Gaussian. And then you run a sampler based on your observational data and compare it to your model at every step, and from that build up your posterior. And because of these restrictions, we typically require that the data in this case that we're using is a summary statistic, so the power spectrum, for example. But it's hard in this framework to model higher order statistics that we need really good theory for, and it's also hard to understand how the plethora of systematics we have might affect these especially higher order statistics. So an alternative that we heard a little bit about from Urosh earlier is simulation-based inference. So the diagram looks a little different here. In this case, we still need to define some broad prior space, but then all we need is a simulator from which we can sample, take a point in our prior space, simulate what our data looks like at that point, and then we train some density estimator to then directly estimate our posterior conditioned on an observation. And in this case, we just need a forward model of our data. And so we are not limited by this modeling difficulty of the summary statistics. So it naturally is nice for understanding or testing higher order statistics as well as potentially full field. And we can forward model the systematic effects that we think are in our data sets, which may end up being a more kind of robust and an easy way going forward. And also, we don't have to assume our likelihood is Gaussian, which is especially important for these higher order statistics or full field where we don't expect Gaussianity. However, this picture of simulation-based inference is limited by the number of training simulations that we have. So if we're gonna, fully forward model our simulation, we need to do it for each, a big range of possible cosmologies and galaxy formation models that we think might represent our universe. And these simulations, as we know, for cosmology are expensive. So how do we get around this? We are creating this new library of mock catalogs called muchisimocks, which translates to many mocks, portmanteaued in Spanish. I should say this is work with the group I was previously in DIPC in Spain. Instead of having to run 100,000 cosmological simulations, which I think collectively in this room we would not have the computational power for at the moment, at the volume we need, we instead use this full field emulator of the matter density field called map, which was created by Drew Jameson. And what it does is it takes a Zeldovich approximation initial condition field and then predicts the n-body displacement and velocity fields from that. So this was trained on pairs of these Zeldovich and n-body fields from the Quixote suite of simulations, which you might be familiar with. It's got 1,000 simulations in the fiducial Latin hypercube, spanning 5 different cosmological parameters at a gigaparsec volume. So that's enough to fit a little chunk of your survey, at least for now. And the nice thing about map is that compared to other approximate n-body solvers, it is more accurate down to smaller scales. So we maintain percent level accuracy down to k of 1. So this is going to allow us to push down to smaller scales in our inference. And this still does take a few minutes per emulated field. So this is why it's not fast enough to run in an MCMC chain to do full sampling, but it's fast enough to create a large suite of simulations that then you can do simulation-based inference on. Okay, so this is just to get the dark matter field. Then how do we model our galaxies that are actually the data that we're collecting? We use something called the hybrid Lagrangian bias expansion. So the idea behind this is that we can break down our galaxy density field into fields at a given order that represent different um, terms. So you can see here we have just our homogeneous field, and then you can break it down into your density term, its tidal field, Laplacian, et cetera. And this has been shown, this is to second order, has been shown to represent the galaxy field quite well as just a field of biased tracers. And then we can advect this Lagrangian space field to Eulerian space. And then all we need to do is weight these different fields based on these bias coefficients, of which there are 4 here. And those represent your uncertainties about galaxy formation. So each of those will change based on the galaxy sample you're modeling and our beliefs about galaxy formation. But this is a pretty kind of flexible and somewhat conservative model of how to populate galaxies onto your dark matter field. All right, so what we end up with here is we run a suite of 10,000 of these emulated n-body simulations and compute the 5 bias fields for each of those. And then we can recombine those with any combination of the bias coefficients to get a galaxy density field. And this is in a Latin hypercube of 5 cosmological parameters. I missed an S there. And then each of these maintains the volume of the Quixote simulations of 1 gigaparsec, but we cut out the small scale modes because we are storage limited. So we are good down to the Nyquist frequency of around K of 0.4.5. And so our suite takes up a terabyte of data, which is fairly reasonable as simulations go, and we could generate more. It doesn't take long. It's more about storage limitations. All right, so now we go ahead and do simulation-based inference with our library of mocks. And so we have 10,000 training cosmologies, as I mentioned, and I populate each of those with 20 sets of bias parameters. So we end up with 200,000 training simulations. I know I said 100,000, but factor of 2 in astronomical terms is pretty good. And those are not completely independent because they're based on the same 10,000 cosmologies, but I'll show you in a minute that that does really help us to populate each one with 20. And then we test this on an independent set of test set that is in the distribution of the training set. And I'm showing here our results on 3 key parameters, so omega m and sigma 8, which are the 2 cosmological parameters that we really have constraining power over from just galaxy clustering, as well as linear bias. And in the blue, I'm showing you the constraints with just the power spectrum. We also include the bispectrum in red, and then their combination in purple. And you can see that we get pretty nice unbiased constraints, and we increase our precision significantly when we include the bispectrum. All right, and I want to briefly show you the effect of the different numbers of training cosmologies and galaxy bias models, because that's kind of a key use of this suite, is to kind of test how many simulations we actually really need to do proper simulation-based inference. So we show here that it's really important to add more galaxy bias models to fully marginalize over galaxy formation uncertainties. So this is if we only use 1 up here, and that's just not converged at all. Whereas when we use 20 and go all the way to about 6,000 out of 10,000 cosmologies, we start converging. This is for the power spectrum, and that story holds up for the bispectrum and the combination as well. A little hard to tell if we're fully converged at 10,000 cosmologies because of noise, but it seems at least there's a bit of a plateau. All right, and very briefly, we perform an out of distribution test, which is really key. So instead of just testing on the same forward model, we test on a mock set that was built with a high resolution n-body simulation and populated with subhalo abundance matching galaxies. So totally different model of how galaxies might populate dark matter. And we end up with unbiased constraints on cosmology up here. You can also see how the bias parameters get constrained and how the bispectrum significantly improves our constraints on the bias parameters, which somewhat propagates to the cosmological parameters. All right, and I will conclude with, we have this suite of 10,000 emulated density fields that we call muchisimocks, and they are useful for simulation-based inference. I'll state broadly that we're thinking of this as kind of a test ground for various high order statistics you might want to try out, and understanding the limitations of SPI and full field inference, for instance, could also be useful for other things such as velocity reconstruction. So if you have ideas, please chat. And this is work in progress. We're continuing our analyses. So thank you for listening. Currently, this is in real space, but we are working on the redshift space analysis too. We have the velocity, emulated velocity fields as well. Right. So we've tested the power spectrum and bispectrum that seem pretty robust down to the Ks we're going to second order. But if we'd want to go to higher order statistics or full field, I think we would need to test the robustness to third order, or we could even use the same approach and actually go to third order. We just would need many more fields to store. So. Yeah, I believe that's true. And we're working now at redshift of 0, although in theory you could extend it to higher redshift and then you would need to definitely take those into account. Yeah, that's correct.
Also, the volume is very tiny. They're using the bigger volume. Then you start seeing the
Right, but we have the nonlinear matter distribution, so yeah, right. Yeah, I think that does help. But if anyone from Fabian's group wants to shout out. Right, yeah, so we just use a stochastic noise term to, we don't do density dependent noise. We just add a noise field and marginalize over the amplitude of it. Cool, I should cite that, thanks. Yeah, I know that, I shouldn't put on this.
Thank you, Marco. Hi, I'm Ivana Nikolac. I'm a PhD student working with Fabian Schmidt and Beatrice Tucci at Max Planck for Astrophysics in Garching. And today, as Marco said, I will be talking about how we can connect field level and summary statistics from galaxy clusterings. I think this way. Okay, our group works on using state-of-the-art inference techniques to extract cosmological and bias parameters from 3D map of a galaxy distribution. And the state-of-the-art approach is to compress the data into summary statistics, namely endpoint functions such as 2- and 3-point correlation functions or their counterparts in Fourier space, power spectrum, and bispectrum. But if we want to extract information in going to the non-linear regime, we need higher order endpoint functions. This leads to difficulties, mostly because of the size of the data vector that increases rapidly with the higher n. And then an alternative approach is to use the full field level of information, where we aim to extract the joint posterior of initial conditions, cosmological parameters, bias operators, and then do field level inference, right? This leads us then to a question of